So here's my code. In this particular example, I'm thinking of a very simple data set where we've just got 3 data points. So 3 values of the independent variable and 3 values of the dependent variable. And then with those 3 data points, we're going to find the unique interpolating polynomial that goes through those data points. I picked this simple case because our intuition immediately will tell us what will go through those data points, so we can check our intuition. Okay, so I'm going to use some linear algebra. That was one way we can solve this problem, so I need to import that package. I'm going to use this SciPy interpolation package, so I need to import that package. And I want to do some plotting, obviously, so I'm going to import matplotlib. This first cell here, this is where I'm just going to define my set of data points. So as I said, I'm just going to think of a very simple case where I just have 3 data points. So n is just the number of data points. And xi are the independent variable. And so again, I kept it simple. My values of xi are just 1, 2, and 3. And then the yi's are the dependent variable. And the corresponding values of yi are 1, 4, and 9. And so look, immediately it's obvious that in this particular case, I just picked the y equals x squared. And I use that to generate 3 data points with x equals 1, 2, and 3. And therefore, y is 1 squared 1, 2 squared 4, and 3 squared 9. So those are my data points. And I then also defined or declared, in addition to the xi, yi, which are just the discrete data points, a array x and array y that I'm going to think of as kind of the continuous independent variable and the continuous dependent variable that's going to be the interpolating polynomial. So of course, in Python on the computer, they're not continuous variables, but I'm making them very, very finely spaced steps in x, very, very smoothly spaced steps in y. So they're the sort of my computer version of the interpolating function. And I could make that finer and finer and finer, however fine I need to make it. So that's think of the x and the y as the smooth independent variable, and the smooth interpolating function. That's the dependent function. Okay, so here I just plot, and it's silly. I just plotted the 3 data points. So horizontally, I've got the dependent variable x, 1, 2, and 3, and then vertically, I got the dependent variable yi, so 1, 4, and 9. Okay, so this cell here, this next cell here is the first method for finding the interpolating polynomial that passes through those data points. So this is the method that uses the linear algebra. Remember, we constructed that a relationship between the measured values for the independent dependent variables that looked like the product of a matrix and a column vector of the coefficients of the polynomial, equals the resulting values for the dependent variable. So m times a equals y. So this guy here. So in this solution, firstly, I'm going to construct that van der Monde matrix, that interpolating matrix. So if you recall, that matrix has dimensions that corresponds to the number of data points that you have. So I've got 3 data points. So it's going to have a dimension, it's going to be a 3 by 3 matrix. And the columns of the matrix are increasing powers of x. So if we look at the matrix, so here I'm constructing a matrix with this column stack. So it stacks together columns. And in the arguments of column stack are what I'm going to stack in those columns. The right-hand column is just a series of ones. So it's going to be a series of 3 ones. And n is 3. And then the center stack is just that independent variable, xi's, so there's 3 values of xi. And then the left-hand stack is xi squared, the 3 values of xi squared. If we had 4 data points, then we'd have an xi cubed term. If we have 5 data points, we'd have xi to the power 4 term. So this is my matrix. And then I've just got to solve the problem. And if you remember, we wrote out the problem here. We want to solve this linear algebra equation for the value of a, which corresponds to the coefficients of the interpolating polynomial. And in that linear algebra package, there is this function solve. We met this once before when we were doing fitting, that allows you to solve this form of linear algebra equation for this vector A. And so you just pass to solve the matrix, the vector over here on the right-hand side of the equation, and it returns to you the solution for A, which in our case is the coefficients of the polynomial. So once I've got the coefficients of the polynomial, so A is a vector that has 3 elements that corresponds to the 3 coefficients of the polynomial. I can actually construct the interpolating polynomial itself. Here I'm doing that by multiplying the different terms in the polynomial. So there's an x to the 0 term, x to the 1 term, x squared term, by the corresponding coefficients to form that interpolating polynomial. So let's just run that. And so if you look at this plot now, in magenta are my 3 data points again, but in green, the green line is this, I'm plotting this interpolated polynomial. And you see that it's going exactly through the three data points. And as I say, it's just one line here in linear algebra in Python to solve for the coefficients of the polynomial, and then just one second line here to construct that polynomial. Here, I put in a little print statement. I just wanted to double check that in this equation that we solved, linear equation that we solved, if we do multiply this matrix by this vector A, which we've now calculated, we do get the original data points. So this product of M and A does equal the data points. So using this numpy function, made the product of the matrix and the vector, and printed the resulting vector out. Its values 1, 4, and 9. And it is indeed our dependent variable, the 1, 4, and 9, the yi's. So that was just a check that the values of the coefficients made some sense. Okay. This next cell is the second way we talked about calculating an interpolating polynomial that uses a set of basis polynomials, Lagrange basis polynomials, as kind of the building blocks for constructing or building the interpolating polynomial. So in this cell, if you have 3 data points, you're going to construct your interpolating polynomial out of 3 Lagrange polynomials. If you had 10 data points, you would construct your interpolating polynomial out of 10 Lagrange polynomials. If you had 2 data points, you would need 2 Lagrange polynomials to construct your interpolating polynomial. I got 3 data points, so I need the first 3. I need 3 Lagrange polynomials, and so that's the first step in this solution here. So let's just look at one of these lines here. This polynomial is, if you remember back to the equation for the polynomial, it was a product of n minus 1 terms, where n is the number of data points. So if you got data points from 0 to n, it's a product of, and you want the ith polynomial, then it's a product of each of those terms from 0 to n, except the ith one. So let me show you how that works out for the Lagrange polynomials that we need to construct here. So this is the Lagrange polynomial. On the earlier slide, I would call this C0. And then this one is C1, this one is C2. These are the 3 polynomials we need. If we're calculating C0, it's going to be the product of 2 terms, that's 3 minus 1. So 2 terms, here's the first term, here's the second term. The xm's in these terms are either m is 1, here you see m is 1, or m is 2. Here you see the m equals 2. And the x0 here, the 0 corresponds to the fact that we're calculating the C0 polynomial, the Lagrange polynomial of index 0. And so that's this guy here. And it's the same sort of pattern for the next Lagrange polynomial. Look, we've gone from calculating the 0th polynomial to the first Lagrange polynomial. So what has changed is that, let's see, this labels xi0 has changed to xi1. This xi0 has changed to xi1. And then you see either 2s for the other xi's or zeros for the other xi's, because we're calculating the Lagrange polynomial for I equals 1. So that's the pattern there. And then there's a similar pattern down here. If you look down here, it's in this column. This column here matches the order of the Lagrange basis polynomial. And this column here matches the order of the Lagrange basis polynomial. And the other xi's are the ones that are not, have m values that are different from that I value. Okay, but anyway, there's a lot of words. It's hard to describe these polynomials. But we've made these 3 polynomials now. Remember, they're made out of this x is essentially a variable. It's the independent variable. and then the other quantities are the data points. So those are numbers. So think of this really as a polynomial made out of a variable and the independent variable data points. Once you got that, you construct the interpolating polynomial by just blending together the Lagrange polynomials. So there's 3 of them here: Lagrange polynomial 2, Lagrange polynomial 1, Lagrange polynomial 0. Blend them together in proportions given by the values of the dependent variable, the yi's. And so this is the second step in the calculation of the interpolating polynomial. And so if you think about this as a totally different approach, right, to the last case. Last case, we used some linear algebra, matrices and vectors. In this case, we're using a special set of Lagrange basis polynomials to construct as kind of the building blocks, the Lego blocks for the interpolating polynomial. So let's just run this. If we again plot the data points in magenta and then plot here the interpolating polynomial as the green line, you find you get exactly the same interpolating polynomial that goes through the data points. And so that's just those 2 cases using the linear algebra method, using the Lagrange basis polynomial method, just saying that, well, you could do either way. And if you come up with a polynomial that goes through the data points, then that is the unique polynomial that goes through the data points. Okay, third approach. So this third approach is just to call a library function that returns to you the interpolating polynomial. And we're using this library function in the SciPy library. So if you remember, I ported the SciPy library package interpolate as under this name here, interpolate. So this cell shows you, firstly, how easy it is to use SciPy to do an interpolation, which you would normally do. It also is interesting in that in the previous 2 examples, when I wanted to plot the interpolating polynomial, I actually constructed it out of a very finely spaced array of dependent and independent variables. When we look at the SciPy package interpolating polynomial, it actually returns an object that is the polynomial. So it's returning something different from an array of X and Y values that interpolate the data. It's returning a polynomial object. And we'll see what that polynomial object looks like. We'll see how we can work with that polynomial object. Okay, so the solution of the problem is just in this one line here. So we call this Lagrange function in this SciPy package. We call it with the data points, so the xi's and the yi's. So remember, this xi is an array of 3 dependent variables, the y is an array of 3 dependent variables. So it knows the size of the array. So it knows the size of the polynomial based on the interpolation theorem that would it would need to exactly match the data. It returns this guy here. I just called it poly, the polynomial. And this guy here is a polynomial object. So it's a programming object that contains data and allows functions that allow you to do various things with this polynomial object. So for example, just to get us used to it, here I'm going to print out the object itself. So I just print poly. And here, I'm going to evaluate the polynomial at the value of x of 2, and I'm going to evaluate the polynomial at the value of x of 5. So let's just run that and look at the print statements first. So written slightly awkwardly here, but here's the interpolating polynomial. So this is, if you say print poly, it prints 1x squared. Well, 1x squared is the polynomial of x that passes exactly through those 3 data points. It's how we constructed those 3 data points. So that is the interpolating polynomial. It is simply y equals x squared. In the second print statement, if I give the argument of poly some numerical value, it takes that as the x value and returns to you the corresponding y value. So if I pass 2, it's going to return 4, x squared. And if I pass 5, which is outside the range of our data points, it's going to return 25, so x squared. And so that's what this poly object looks like. Here, for the purposes of plotting it, I gave the poly object the argument x, which, as you remember, was a finely spaced array of x values that we were using to represent the continuous x, approximately. If I could pass it x as the argument, it's going to return the corresponding y values. So the corresponding values are the values we will plot again. And so then I just plot, finally, make this plot one more time. Again, magenta are the data points, and green is the interpolating polynomial. And again, we see this method gives us a smooth function polynomial that passes through the 3 data points exactly.